Okay, anyway, so the theorem is there is one-to-one correspondence between the following two types of data. So first, a junction we have just the process of the symbols. So this will see so in the proof proposal, you can notice the one version you already know from the previous section. So that A implies B, you already know. That was the lemma that we proved at the very end of the previous lecture. So we can now focus on the proof in that direction. So for the proof in that direction, it was working. So let's say A. So object D, this set. Essentially giving the solution for an arrow, so we set epsilon sub D to be a map D. So this convolutional calculus applied to object D and D. So we set this epsilon sub D to be unique map. So continue to call arrows negatively maps. Both arrows from this map. So such that set this to be unique map. So this is the map from G, that applies to G. Epsilon sub G of G. So this is a map in the computer. So maybe it's easier to understand this if I draw this as a little bit variable that you use the map. So where is this coming from? I know this property, this is the universal arrow. Now this is true for any object C. So I'm choosing object C to be G of D. And now, so this will be the arrow that we know that we just universal for this thing. And it means that this initial object is a category. So this is what is in the category, so there is the unique section of this. So this is the reason why I can say that there is a unique map. That's what's happening. So if there are any questions, you can ask me right now before we continue. So again, because I look at the definition of universal arrow, that's an initial object. So this is the initial object for object for C, which is G of D. Hence, there is a unique map here. Remember that the map with the corner category is exactly map here, such that we can make a map of G. This is supposed to be by the definition of the initial object. Yeah, and I still have several steps that we need to do. So let me give these steps some names. So first step is so I want to know that it's not just the map given object. I want to know actually that epsilon, all such components together form a natural transformation between this composition of functors and the identity functor. So this is the goal of the next step. And the proof it will be by looking at the same time at two commutative diagrams. So let me just draw these commutative diagrams. So the beginning of the first one is just the same triangle, but I'm going to just rotate this and reflect. So just to draw the same thing a little bit differently. So here we have identity. So the same thing at the moment. And then I'm going to add one more ingredient. This is G of Q, the G of the D prime, and here we have G of the Q prime. So here I assume that I have this map Q from D to D prime. So at least this part explains what we have here. And then again I use the property, this is an initial object, hence there is a unique Q prime that I can construct and make this whole big triangle commutative. Okay, so this is one diagram. And let's also look at another diagram, which also consists of two pieces. So the first piece is just the fact represented by a diagram that eta is a natural transformation. Okay, there shouldn't be any surprises here, right? If I don't have any mistakes, I hope I don't have any mistakes here. So then we again add one more triangle. So we add additional arrow, which is G of the epsilon D prime. And again, identity here. So the same triangle as before, but for the object D prime. Yeah, there is a mistake here actually. This is D prime. Okay, so now if I look at these two diagrams, I can conclude. So maybe so Q composition with the epsilon sub D is equal to the epsilon sub D prime composition with the F G of Q. So this is a conclusion that I can see looking at these two diagrams. So maybe let's pause for several seconds. Do you see how we can look at this diagram and draw this conclusion? Well, in both diagrams, we have an initial object in the comma category, right? And we have a map to precisely the same object in this comma category, namely this object, this diagram. So because, well, here take composition with the identity, but it doesn't change anything.
And from the initial object to any other object, there is only one map. And in this case, this map is the composition of the epsilon sub d and q. And in this case, this is composition of the fg of q and the epsilon d prime. Hence, because this is unique object, these two maps has to be the same. Okay? Questions maybe? Okay, if there are no questions, I continue my computation. Well, actually, I'm pretty much done with this step, right? Because if I have this formula, this is precisely the statement that the epsilon, so all these components epsilon d, form a natural transformation, right? That's precisely the meaning of this formula. So that's a natural transformation. And let me call the next step second triangle identity. So at the moment we have only one triangle identity, which is more or less given by construction, and we need to show that there is one more. Again, the proof will be more or less the same as the previous proof. I need to look at two diagrams and then use uniqueness and draw the conclusion. So here in this case, the first diagram is very simple. I have C, eta sub C to the GF of C. Here I have G applied to the identity for the object f of C, GF of C, eta sub C. Well, clearly this is a commutative square, sorry, commutative triangle. And another diagram, I think I need to use another blackboard to this diagram. It's a little bit larger. So the second diagram. Again, maybe let me just finish the diagram and then I explain. So the beginning of this diagram, namely this commutative square, is just, again, the statement that the eta is a natural transformation. Now, additional triangle that I need in this diagram contains G of the epsilon f of C to the GF of C and identity here. So pretty much the same reasoning, looking at the two diagrams, noticing that we know that this is an initial, what's initial? So this is the initial object, and we have with this map to another object, which is just this composition, right? So this map from the initial object to the other object has to be unique. Hence, the conclusion is in that case, that map is just the identity. So identity on the f of C is the composition of the epsilon sub f of C composed with the f of the eta sub C.
May I ask, may it be the case that G and Q of C in the middle of the diagram is some mistake? I don't understand why it's there.
Oh, you mean over here or where?
Right, yes.
Here?
Because we need
Ah.
to
Yeah.
apply marquism G of the C. Okay.
Thank you. Okay, but anyway, so this last formula is exactly the second triangle identity. So there is only one more step left in this proof. So I'm going to call this last step uniqueness. So uniqueness. So I know that to have a junction between two functors is the same thing as to have unit of the adjunction for unit of the adjunction satisfying two triangle identities. So I somehow constructed, and this of course need to be uniquely defined data. So somehow I constructed the unit and co-unit of the adjunction. I checked two triangle identities, but there is a question what to do if I have the following. So if I have epsilon and some maybe epsilon prime constructed by some different procedure, so from the composition Fg to the identity functor on C, such that pair eta epsilon and eta epsilon prime both satisfy triangle identities. Okay, so we can look at the commutative triangle. So we have this commutative triangle, and the meaning of this triangle, well, it's exactly the same thing as saying that the epsilon sub d is a map between f g of d eta sub g of d. So this is one object in the comma category to another object in the comma category, which is d1 sub g of d. Okay, so this is what we get for the epsilon sub d, but the same, so the same works for the epsilon prime sub d. Right, so both epsilon and epsilon prime give me a map from the initial object to this object. Hence, this map is unique, and epsilon d is the same as the epsilon prime d, or any d. And that's the end of the proof. So this finishes the first way to describe a junction between functors. And so from now on we're going to do a little bit different things. I'm going to do one example about adjunctions, and then we're going to do limits. So I just want to say that if you don't really understand this third interpretation and this proof, it's not really a big deal for this course. I'm not going to use this. But I mean, the purpose was you can read different texts that using category theory, and in some texts people just use the third definition. So it's useful to know this, but it's not what will be important in this course. Okay, so I want to do an example. So this will be the last thing that I'm going to do in the first chapter. An example I want to say is quite important. I think for me this is maybe the most important example of adjoint functors in algebra. So it doesn't matter which algebra you do, commutative algebra, non-commutative algebra, representation theory or something. It's still an important example of adjunction. So example, home tensor adjunction and the change of scalars. So the assumption is that we have two rings, so R and S are rings. So associative rings, not necessarily commutative, with the multiplicative identities. And then I need a bimodule, so B. And to indicate where R and S is acting, I'm going to write it like this. So this is a bimodule. So do I need to remind you the definition of a bimodule? Well, maybe if you don't explicitly ask me to do this, but I still do this, but without writing anything on the blackboard. So this means this is an abelian group, right, on which the ring R is acting on the left. This is why I'm writing R on the left. There is an action of the ring S on the right. And the additional last axiom in the definition of a bimodule, these two actions commute. No, in the sense that this is associative. You can, if you have an expression like this, it doesn't mean how you put parentheses. You can put them around R and B or B and S. So that's a bimodule. And the equivalent way to say that this is a bimodule, so again, remark in parentheses, or R tensor as opposite module. That's precisely the same data. To have a bimodule is the same thing as have module over this tensor product of two associative rings. So then we have an adjunction. F, we have category of S modules, left modules in this case. There is of course a version for the right modules without much changes, so let's consider left modules. So functors F and G from left modules over S to left modules over R. Here, by definition, I'm saying that F on some S module is just a tensor product with a bimodule. Right? You can notice this makes sense, right? Because if you're computing tensor product over not necessarily commutative ring, you need to have one module to be right module, which is, left module, in which in this case this is M, and another module to be an S module. In this case, this is left module over S, and this is B. And when you compute this tensor product, you use this right S module structure. Right? In general, if you take a tensor product of a left and right module, the answer is just an abelian group. But additionally, here we have the left action of the R on the B. Right? So, in fact, this is not just an abelian group, this is indeed an object in the category of R modules, left R modules. So that's a functor F, and the functor G is, on some module N. This is home from this bimodule to the given module N. Again, you can easily notice that this definition makes sense, right? Because when you compute home, you indeed need two left modules or two right modules. So N is a left module, B over R is a left module. So everything is okay here. And when you compute this home, again, in general, home between two left modules is just an abelian group. But here, additionally, on B, we have the right S module structure. So it means that I can act by the string on the right on the B, but when I compute home, we know that home in the first argument is contravariant, so this whole thing will be a left S module. So using all these kind of trivial remarks, you can see that indeed these are two functors, and there is an adjunction between these two functors. So let me write F is left adjoint to G. So in other words, we have the very useful algebraic adjunction, which is called home tensor adjunction. was not enough space. Home. So this home is supposed to be the second argument in the home over S. And if we want to see why there is such an isomorphism of two homes, well, it's easy to come up with the kind of explicit formulas. So for example, if you take F to be in the home on the left, you just take this F and send this to the following. Right, so from this F, which is some homomorphism of R modules, I'm supposed to get a homomorphism in this kind of modules. But let me just write like this. So element M from the module M goes to the following map. So F applied to the tensor product of the blank and the element little m. Okay? Does it make sense, this definition of the map? Right, so I know if I have F, I know how to compute this F on a tensor, well, say on a simple tensor, then we can always extend by the additivity, where you have a element from the B and element from the M. So here, for the fixed element M, right, I can send this to this map, which will be, if I take an element from the B, I can plug in this element from the B into this formula, apply F, and then I'll get a kind of element in the N. So this is one way to go in the other direction. Now let me assume that I have also map G from the home on the right, and this G can be sent to the following map. So on the simple tensors, on the simple tensor B tensor M, this is a map that sends this simple tensor to the G of M evaluated on the B. Again, it makes sense because whenever you have element G, if you compute this G on element from the module M, you still get some homomorphism, right? And you can compute this homomorphism on the element B, and when you do this, you'll get some answer, which is an element in N. So at least it makes sense. So I think the formulas make sense. And I'm going to leave, I think it's quite boring whenever you have these formulas, it's quite boring to check that these two maps are inverse to each other, and this map is actually the map of modules. So all the details are exercise. So exercise. Check that these are maps of modules inverse to each other. So that's the adjunction between home and tensor. So now let's consider a situation where I have F, a map of rings. So then there is a standard functor. Oh, there are plenty notations for this functor. So F with the upper star, also res for the restriction along the homomorphism F, and sometimes res where you use S and R. And this is just a functor which restricts the scalars. So you take an S module, left S module, and by this homomorphism F, you can act with elements on the ring R, right? You take an element in the ring R, you apply F, you get something in the S, and you use this element to act on the abelian group, which represents the left S module. So this gives you a left R module. And this is the restriction of scalars. So the functor of restriction of scalars. It's quite elementary exercise to check that this is indeed the functor, so that that on the maps of modules is also well defined. So interesting that I can write this functor, so f, so I'm going to use the first notation, f with the upper star of the n. You can write this as a home over the ring S, where the first argument is the bimodulo S, where I put left S, well, S modulo structure on the left and R modulo structure on the right. And also I can write this as a tensor product with the bimodulo S, where I put the modulo structures the other way around, and again take a tensor product with n. Okay, so of course whenever you have a homomorphism of rings, this is automatically give you on the second ring the structure of a bimodulo, and in fact you can even find two bimodulo structures. Like for example here I consider S as the left modulo over S, I consider R as a right modulo over R, and then I can also consider S as a right modulo over R, and the action is exactly by this map F. Yes?
What does F the star mean?
Hmm?
What F the star? No, but that's следующее.
This is the restriction of scalars. Restriction of scalars. So I'm taking an S module, right? I know this is an abelian group on which I can act with the elements from the S.
Yes.
So now I can take the same abelian group and act on this abelian group by the elements from the R. I'm taking element from this ring R, I apply F to it, I get something from the S, and I use with this, act with this element. So this is the same thing as, for example, the very basic example of restriction of scalars is when you have, I don't know, real numbers and complex numbers, right? So then whenever you have a module over the complex numbers, which is just the complex vector space, you can automatically consider this as a vector space over reals, right, just by restricting of scalars. And this is quite a general thing that makes sense for any homomorphism of any two associative rings. So this is what I'm doing here. Okay. So I want to say that these two particular isomorphisms are rather trivial if you just think what you do here. Definitely, well, what you need to do just restriction of scalars and this Holmes and this tensor product and give you exactly this. So, but using these two interpretations, I can notice the following. If I introduce the functor f with a lower shriek, or also known as the induction functor along homomorphism f, or another notation, induction from S to R, so that would be a map from the R modules to the S modules. And by definition, f with a lower shriek of the module M is a tensor product so it's a tensor product with the S, which I interpret as a bimodule, so tensor product over R. Now, maybe it's also important to notice that this tensor product over S. So I consider S as a bimodule and use the right R module structure to compute this tensor product. So what's left is the left S module structure. So that's. Well, the structure of this bimodule depends on F. The structure of this bimodule depends on F, right? To know that S is the right module over R, I need some additional information, and in this case, it's just homomorphism F. Okay.
What does int stands
For induction.
for?
Yeah. So perhaps when you study representation theory of finite groups, you saw this operation of induction. So that this construction will be just the most general version of that induction for the representation theory of finite groups. So, but the point why I'm doing here, of course, I have an adjunction between these functors. So one is the restriction of scalars, and the other is the induction. So let's check this. This is quite simple computation now. So home over the ring S from the induction f lower shriek of M to the N. Well, just plug in the definition. This is hom over S tensor. So the first argument is the tensor product of the S, M, and N. So the second argument is N. Now use the adjunction to write this as the hom now over the ring R. Notice that in the adjunction, indeed, we need to change for this outer hom, we need to change the R and S. So we need to change the ring. So this will be hom over R. So the first argument is M. And the second argument is the hom over S, 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 R, tensor product. No, there's no tensor product. N. Which is, again, just plug in the formula, one of the formulas for the F upper star, namely the first formula. We'll get the hom over R and F upper star open. Okay, so from this formula we can see that the F lower shriek is the left adjoint to the F upper star. Okay, that's indeed what we proved in the last sequence of computations. But in fact, for this F upper star, which is the restriction of scalars, there is not only the left adjoint, there is also right adjoint. And this is called the co-induction. So notation is F with the lower star. So F with the lower star of some modulo M, which is co-induction. Notation is the same as for induction. So that's a functor from the R modules to the S modules. And by definition, this is the hom over the ring R between bimodulo S and modulo M. So bimodulo S, in this hom we use the left R module structure. Well, maybe I'll just leave this as an exercise. It's more or less the same computation as we have in these two lines, is to check that, so exercise, that the co-induction is the right adjoint for the restriction of scalars. So that's a general algebraic example where you have a functor, restriction of scalars, and this functor has the left adjoint and the right adjoint, which is quite exceptional situation. Not so many functors that are useful and also have left and right adjoint. Okay. And with this section, I want to finish, sorry, with this example, I want to finish this section about adjoint functors and also finish first chapter and go to the second chapter about limits and colimits. Okay, so first section, we just discussed the examples and then general definition of the limits. So my plan for the limits and colimits is kind of dual to each other. Whenever I know something about limits, usually can say more or less the same thing about the colimits, just going to the opposite category. So my plan is to start with some understandable example of limits, and then from this understandable examples like products, equalizers, pullbacks, kind of generalize this to a general definition. And then for the colimits, I'm going just to give you a general definition and then look at several examples. So the first situation is the binary products. So this is probably the simplest possible example of a limit. So definition. So let x and y be two objects in some category C. A product. So x and y. So formally speaking, the product is a triple. So is a triple where I have an object which is just denoted usual as a product of x and y, and I have two projections, pi 1 and pi 2. But of course, this is just a formal definition, but whenever you do some computations, you usually don't write this as a triple, you just write this as a product of x and y. But it's important to understand that, in fact, these two maps are also part of the definition. So in other words, I have object, which I'm going to call the product, and from this object I have two canonical projections, to the x and to the y. So I'm going to call this pi 1, pi 2. So maps pi 1 and pi 2 are called canonical projections. For this product. So this is just a description of the data that we have, but what's actually the definition? Well, this is supposed to be a triple with a universal property, so such that for any other triple, so for any object T, two maps, which I'm going to call F1 and F2 from T, so F1 from the T to the X, F2 from the T to the Y. So for any such other triple, there is a unique map F. Sometimes people write this in terms of components as F1 and F2 in braces, no, in angles. So such that F1 is the composition of the pi 1 and F, and F2 is the composition of the pi 2 and F, which is much easier to illustrate and see on the diagram. So I have one diagram, and I have another diagram for the product. Right, so in the product, I have the product of two objects, two canonical projections, and whenever I have a diagram of the same form, there is a unique map F here, such that both triangles are commutative. And the commutativity of these two triangles is just these two formulas. Okay. So another point of view on the product is the following. The product is a terminal object. I promised you that more or less what we're going to study is terminal and initial objects and some categories that we're going to construct from the given data. So product is also an example of some terminal object. Now, in the category, with objects being just such triples. Right, so the triple is just, so in this case, of course, I assume that x and y are fixed, and the objects in this category are triples in precisely of this form. There is some object T in the middle, and there are two maps, F1 and F2. So these are the objects, and what are the maps? Well, the maps are also what you expect them to be, right? So whenever I have one such diagram with T, F1, F2, so these are maps to the x and y, and there is another diagram with S in the middle and same maps G1 and G2. Then the map say, map from the S to the T, such that these two triangles are commutative. So of course we can notice that with this definition of a category, it's just a restatement that product is the same thing as the terminal object. So before we look at the several examples, I can formulate several remarks. So let's exercise this. So the first thing that you can notice is that if you look at the home set in the category from some object T to the product of the X and Y, this will be the product of homes from T to X, and then I take a product from, sorry, and then I take the homes from T to Y, right?
What is this?
Any category. So given a category, well, of course you need to know that from the definition, it doesn't follow that the products exist, right?
By the X times Y, you mean the object from the first element from the triple.
Yes, exactly. So I'm taking some category. I'm assuming that this is such a category that I have binary products. Again, not every category has binary products. We will see examples probably next week. And here, this is the first object in that formal definition, right, in the triple. And notice that here, this is a product in the just a standard Cartesian product of the sets. Right, so on the right, between the well, on the left and on the right on the product, we have just two sets. So we know how to take a Cartesian product of two sets.
What relationship to the T?
This is Y. So
X times Y?
so this is C, T, and Y.
No, between T and C.
Between T and T.
X related to X division. What is it between?
You mean this part?
Yes.
This is just X.
And after that it's...
And this is a product of sets. This is not X, this is product.
okay. It's called so yeah.
Mhm. Okay, so the second quite elementary remark, which I'm also going to leave as an exercise. So if T in the category C is a terminal object, then the product, again, there is an X and there is a product. The product with the terminal object is the same object that we started with. I hope you can see the difference, right? So this is a product between two objects and this is object X. Well, maybe X is not the best choice for the notation in this case. Okay, and the third remark, maybe I just leave it as a question. Is it true that canonical projections are epimorphisms in any category? Okay, so that's just several general remarks. We can look at the examples of the products, and for example, if you take sets, then I think this is not a surprise. Well, maybe you can tell me what's the product in the category of sets. Yeah, so that's the standard Cartesian product of two sets, and why? Well, we just need to see that this definition is satisfied, right? So if we pretend that this x and y are just two sets, and this is indeed just the Cartesian product, so all the ordered pairs, right? So whenever you have a map from another set T to the x and to the y, how we can define such a map to the Cartesian product? Well, we just do this component-wise, right? And indeed, since these two squares are supposed to be commutative, this commutativity, sorry, not squares, triangles. So commutativity of this triangle automatically tells you what the first component has to be, right? This has to be f applied to the first component, so f applied to some element from the T, and the same for the second one. So this f is uniquely defined. So in the category of sets, product is the Cartesian product. Well, and this category, this example with the sets can be generalized into several directions. Well, for example, we can look at the category of the G sets. So can you tell me the product in the category of G sets? No, you can try to guess it. Yeah, but you also need to specify what the action on the product. Yeah, diagonal, right? Yeah. So let me leave this as a little exercise. If you know the answer, it's not very hard to check small as the same argument as they've done for the sets. So in this case, the product is Cartesian product of sets. Sets with a diagonal action. Well, meaning that if you want to apply element from the group G to the x comma y, this has to be by definition G applied to x comma G applied to y. Okay, so a third example. Well, we can take some algebraic categories. For example, we can take monoids, groups, rings, or commutative rings. More or less using this reasoning with the category sets, we can see that the product in these categories, well, it's just the product of monoids, groups, etc. Just the standard thing. You take Cartesian product of the sets again, right? And whenever, for example, say groups, this is how you define the product of groups in the first semester. You just take the Cartesian product of two groups, and then you define product on this Cartesian product component-wise. So again, you can check that this is indeed a product. And if you do topological examples, that's again, there are no surprises. So say for take topological spaces, again, product in this category is Cartesian product with product topology. So all the examples that you know from the first year topology, first year algebra, are just in fact the examples of something which can be described as a universal property. And even more, say example 5, we can take the category of all categories, and we also define the product of two categories. Well, in the context where I wanted to use some bifunctors, we define binary products of categories. Indeed, you can look at that definition and then check that this is the same as the definition using the universal property. More or less immediately can be reduced to the case of the set, of the category of sets. So these are binary products, the simplest possible limits, and we can generalize them to the situation where you have not just two objects but a set of objects. So definition of a general product so if we have a family of objects parameterized by set I, so this is set of objects in the category C. So a product of this set of objects is, again, formally speaking, there is an object which I denote as a product, and also for each index little I have a canonical projection. So maybe I write it here. Phi I is the canonical projection from the product to the individual component xi. Okay, so such that for any diagram, so in this case we have diagram where we have some object T and maps Fi to the xi, and that is given for all indices I in the set large I. So for any diagram there is a unique map F from the object T to the product with the property that Fi is the composition of the phi I and F. So as you can see, this is a straightforward generalization. If I is a set with two objects, you'll get the previous definition. But this is more general. This is for any set of objects. No, not necessarily countable, for example, quite general. And the standard question about the categories you can ask is that, do you have a binary products or do you have a general products? Or can you give me an example of a category with binary products but without general products? Yeah, finite sets, or you can also take something like finite abelian groups, so where you can take infinite products. But in the nice categories, in the categories, for example, we described in this series of examples, you can actually take all possible products parameterized by all possible sets. There are no restrictions here. Okay. Yeah, so this is some general stuff, but sometimes it's also useful to know that you can not just take product of objects, but product of maps. So definition product of maps. So suppose I have two maps, F from the X to Y, and there is another map G, sorry, not to Y, I want X to the X prime, and G from Y to Y prime. And I want to define the notion of a product of two such maps. Well, I can do this by looking at the diagram. So I take the product of X and Y. So there are two projections, pi 1, so this is to the X. There is pi 2 projection to the Y. Now the same thing with the primes. Okay. So here we have map F, and here we have map G, which are given to us. But now you can just look at these compositions, right? So we have, for example, you know that this bottom line in this diagram is diagram corresponding to the product. Here there is third object, and for this third object there are two maps, right? And clearly, just that there are two maps. We don't need anything else. Then, by the definition of the product, you know that there is a map here between those two objects, and by definition, it's called the product of the map F and map G. So this is how you can use the universal property to define the product of maps. And you can also define the diagonal map categorically. Well, from the point of view of sets and the sets with additional structure, well, this is just a map that takes an element here and sends this to the pair XX, right? But you can do this without elements, just using only stuff from the category theory. You just take the product of X with itself, right? Then take one more copy of X and consider two maps, just the identity and the identity. Hence, there should be a unique map, which I'm going to call the diagonal for the X. So this is a way to define diagonal abstractly. And those things are related. So there is a proposition. So suppose I have map F from the X to Y, and as before, yeah, I think this is correct. I think I changed my notation a little bit. So this is from the X to Y prime, yes. So then there is a relation. If you take F and G in angles, this is the same thing as the product of the F and G. And then you take composition with the diagonal map. So knowing the product of two maps, you can kind of recover this map, which was part of the definition of the product, using the composition with the diagonal. And I want to postpone this proof until the seminar. I think it's not very hard, and you can learn by doing this proof by yourself. So exercise. Now the statement that these two maps coincide, this map is the same as this map. Definitions were a bit different if you, for example, go back to how it was defined. So this is just a product of maps, and that was just a part of the definition of product of two objects. Okay, now let's do another kind of examples, equalizers. So definition, an equalizer of maps F and G. So these two maps have the same domain and codomain. So say in some category C is a pair. Again, formally speaking, I need to say that this is a pair of some object and the map little e. So this map little e is a map in the category from the object e to the x. So such that, so on the diagram we'll have the following. We have object x, object y, between these two objects there are maps F and G, and the equalizer we have E and the map little e. So the situation is the same. We have some kind of diagram, and for this kind of diagram we want to find the kind of universal way to add something to this diagram. So in this case this is just object and the map of objects. Well, the property that you're supposed to have is the following. Suppose you have another object, so let's call maybe this Z, and let's have another map H, right? So with the assumption that a composition of the FH is the same as the composition of the GH, right? And this is what is called that H is equalizing F and G. So when you take a precomposition with H, you get the same maps. So H equalizing F and G. And equalizer is actually universal map with such properties. So whenever you have additional Z and H like this, you have unique map, which I'm going to call H bar. Yeah, by the way, I forgot to tell you about the, when I draw diagrams with the products, when you want to say that from the given data there is a unique map, you usually use this dash notation for this map. So there is unique map H bar. And in formulas there is unique H bar from the Z to the E, such that, well, this triangle is commutative. So H is equal to the E H bar. So the same remark as with the products, that we can understand this as a terminal objects. So an equalizer is a terminal object in category with objects just pairs Z and H, where H is a map from the Z to X, such that we have those conditions. So FH is equal to the GH. Yeah, this remark that this can be interpreted as a terminal object, well, again, I forget to tell you about this when we discuss products, but from this we can see immediately if it exists, it's unique, right? Because terminal object is unique. We don't know in general that we take some category that there are equalizers in this category, but if there are equalizers, they are uniquely defined. And one case of the equalizers, so maybe I formulate again this as several remarks. So first remark, if C has a zero object, remember that the zero object is a initial and final at the same time. So then we can define zero maps for any object. So 0xy. So a zero map is a map that can be factored through a zero object, something that we discussed last week. So then we can define the notion of the kernel of some map. So as before, let's assume that we have map F from X to Y. Then the kernel of the map F is by definition the equalizer. Well, sometimes it's also useful to have notation. So equalizer of the F and G is E. Well, again, formally speaking, I need to say that the equalizer is a pair, but usually the object is important and the map is understood from the context. So in this case, the kernel is the equalizer of the zero map between these objects and the given map F. So that's a categorical definition of a kernel. And you can notice that if you, for example, take category that you already know, like vector spaces or modules over some ring, this will be precisely the standard definition of the kernel of a map. It is equivalent to one that you know from algebra. And the second remark, I don't want to repeat this, but I just say
May I ask why zero object is a morphism?
this is not a zero object, this is zero map.
Zero map.
Yeah. So if you have a zero object, you can define notion of a zero map. That is a map that can be factored through the zero object. This is what we call zero maps.
Okay.
It's like, for example, for vector spaces, well, you can define the notion of the zero vector space, right? But you also can talk about the zero maps between two vector spaces. And in fact, it will be precisely something that can be factored through the zero vector space. So that's in this situation, O x, y is the zero map between two objects. Yeah, so in the second remark, I want you to say that this definition for the products with set of objects, not just two objects, can be generalized for the equalizers. So as before, we can define the notion of equalizer for a family of maps, not just two maps. Okay, so let's look at examples, and probably the most important example is in the category of sets. If you don't understand this example, you won't be able to understand any other examples of equalizers. So what is the equalizer in the category of sets for two maps F and G? You can, yeah, precisely. So this is all the points x in the x such that f of the x is equal to the g of the x. If this wasn't obvious, probably this is something to think about. Maybe we'll start with this example next week, because I'm out of time today. So let's take a break, and then after the break, we will write our first quiz.